In the last video, I said that if it got 5,000 views, then I would present my thesis, or at least a summary of it. And so that video did surpass 5,000 views. Thank you very much. I'm glad you guys are interested. So what I did was I actually don't have a hard copy of my thesis. It's uploaded on the internet, and I also have a PDF copy. But I went to the internet, I downloaded my thesis, and it's funny that I wrote it like a few years ago, so it hasn't been, at the top of my memory banks for the past, few years. But when I started to read through my thesis, it all came, flushing back. And I wrote up essentially the notes of what my paper was about. My paper was roughly 30 pages long, but here I've condensed it down to 2 pages so that you can get the general idea of what we were doing. Okay, so let's start at the beginning. So first off, we define the Gaussian integers to be all of the lattice points in the complex plane, which means that a and b are an integer. And the idea here is that we want to come up with a way to represent any complex number in the plane using a radix expansion. So what does a radix expansion mean? Think about the decimal system. In the decimal system, if I gave you a number like 123, you can write that as 1 times 10 squared plus 2 times 10 to the first plus 3 times 10 to the 0. And any number in base 10, except for the negatives, but you can throw in a negative sign, can be written as a decimal expansion. If you choose binary, then you have digits 0 and 1, and then you have powers of 2, all that good stuff, and you can represent them in base 2. So the idea here is that we want to choose a Gaussian integer as a base for a number system, and then somehow come up with a digit set so that any point in the complex plane can be represented as a radix expansion, which is really just a sum, of the digit times base to a certain power, so on and so forth. It's the same type of construction. And this has been known for quite a while. This has been known since the age of Gauss. So in our paper, it was very convenient to consider bases of this form. I'm not saying that this is the only way to represent it, certainly not. But we looked at bases of this form, negative n plus I, where n was a positive integer bigger than or equal than 2. Okay. So by choosing a base that looks like this, the corresponding digit set can be found to be the numbers 0 through n squared. So we label the digit set D here. So for example, if you choose the base negative 2 plus I, then your digit set would be 0, 1, 2, 3, and 4. If you choose n equal to 3, you'll get 0 through 9, like their normal decimals, digit set. Okay, and so by using these two, you can express any complex number uniquely as a radix expansion, which I denote here, but really this is just the summation of dk times b to the negative k, where dk's are your digits. Now, the sum is from negative infinity to infinity, but in order for this to converge to something meaningful, the parts where you have negative index has to eventually be 0 after a point, right? Because you can't just, keep going and going and going. It would explode. So it has to be a finite number. So another way that you can write this, in positional notation, a lot of times it's called, is that, you have the first n plus 1 digits here, and then everything past here for d negative n minus 1, d negative n minus 2, so on and so forth. All those d's are 0. So this is like the integer part, quote unquote, of z. And then this would be the, I don't want to say decimal part because it's not decimal, but you get the idea. It's the part after the point. So this would be, and I put the b here to denote that I am in, this will be my base b. Okay, so now what? So now what we want to do is construct Cantor sets, and we do it via deleted digit sets. Okay, So we define the set T0 to be the set of all complex numbers of this form. So you have 0 integer part, base b, d1, d2, d3, so on and so forth, where those dk's are your digits. You can think of this as analogous to the unit interval in the complex plane, but it's not the unit interval. It's not the interval from 0 to 1. It's all points in the plane whose radix expansion, looks like 1, so to speak. And the reason we called the set T sub 0 is because when you graph this set, when you graph all these points in the complex plane, I really should have had those pictures with me. I might post it to the community tab on my channel. But when you graph this set T sub 0, you end up getting a tile in the complex plane, and it has a very complicated boundary. It's actually a fractal tile. It's kind of neat to consider what it looks like. And it looks different for base B. So if B is -2 plus I, which was the example we used a lot in the paper, you end up getting a tile that's self-similar up to a factor of 5. So you have 5 digits, 0 through 4. And it's hard to explain without drawing a picture of it. But you get you have the tile, and then when you want to construct it, you shrink it. If you shrink it and then rotate it and then take 5 extra copies of it and tape them together without, a better way to describe it, you end up getting the same tile back. I'll post a picture of it on the channel if I can find a good picture of it. It's kind of neat. But just for the time being, you get a really complicated looking tile. And so now what we do is we define a restricted digit set, which I denote as delta. And we want delta to be separated in the sense that you want to choose digits in the restricted digit set such that they are sufficiently far apart from one another. And we found in our research that the digits are far enough apart from one another, meaning that it has to be bigger than or equal to 2. In the case where n is equal to 2, remember that's this n that's up here. And for n larger than or equal to 3, which I should have written equal to 3 there, but I didn't, then we want to be greater than or equal to 2 times n. Otherwise, because the reason that we wanted it that way is because when n gets large, you get more self-similar pieces, and the angle at which they rotate gets more and more flat. So they get closer and closer together when you remove some of those pieces. You'll see what I mean here in a second. I'm getting ahead of myself. So for the time being, just take it on faith that we need these two conditions for given n. And so what we do now is we inductively define a restricted digit set. Well, not a restricted, what do I call it? A refinement is what we called it in the paper. So we call Tk a refinement of T0, where Tk is the set of all complex numbers in T0, such that the digit dj is in the restricted digit set when j is less than or equal to k. So the first k digits have to be in the restricted digit set, and then everything after that is fair game. It can be anything you want it to be. Okay. And then we define t to be the limit as k tends toward infinity, which can be simplified as the intersection of tk's as k runs from 0 to infinity, because tk is a subset of tk plus 1, and that's true for any k. And it's not too hard to show. You can actually think about it for a second based on this definition that has to make sense. And here in parenthesis, I wrote Cantor tile. We did not call it that in the paper. It's just when I was writing this up, I thought that was a pretty clever name to call it, because it's like a Cantor set. If you're familiar with the middle thirds Cantor set construction, this should be obvious why Cantor was my favorite mathematician in that one video, because of how much research I did with Cantor sets. But here, the set is a tile, so Cantor tile was just a natural thing to call it. Okay, so one more piece of notation. For a fixed zeta in the complex plane, we define the set t plus zeta as the set of all complex numbers of the form z plus zeta, where z is in t. Essentially, what this is just the tile moved over by zeta. That's all it is. It's a translation. Now, given all this information, we're able to state the theorem that was the primary result of my thesis. And I call it the theorem of the struggling grad student. Obviously, I didn't call that in the paper. I'm calling that here now. So if you have a separated restricted digit set delta, d given here, that's all familiar notation. You fix an alpha between 0 and 1. And the theorem says that you can find a zeta in this set F, where F is the set of all zeta, such that T intersected with its translate. So remember how we defined T on the previous page. So you have T, you have a translation of T, and then you intersect the two. So you see where these two sets overlap, and you choose a zeta in the set such that this intersection is not empty. So you're picking for lack of a better term, a translation vector. You can think of zeta as a vector in this case. So what it's saying here is, actually, you know what? I should not have used zeta here. That doesn't make sense. Wait, maybe it does make sense. Hold on a second. There exists a zeta in F. Oh, no. I'm right. Yeah, I copied this right. I got confused here for a second. I thought we were picking stuff inside the intersection, not the translation vector itself. Okay, everything's good. So what this theorem says is that you can pick a zeta in F such that the dimension, so the H stands for Hausdorff, so this is the Hausdorff dimension, of the intersection is equal to alpha times the logarithm base square root n squared plus 1 of the cardinality of delta. And I don't really know why we stated it that way in the paper, because really all it means is the Hausdorff dimension of the intersection is equal to alpha times the Hausdorff dimension of the set T itself. They're equivalent statements, essentially. So what this theorem essentially says is that you can, so no matter, okay, so this number that's over here on the right-hand side, it varies between 0 and the dimension of T. And essentially what this is saying is that given any number between 0 and the dimension of T, you can find a subset of that Cantor tile such that its Hausdorff dimension is equal to that number that you picked over here, more or less. And then the intersection, I should say, the subset that you pick is of a very specific form. It looks like this. Now, in many contexts, the Hausdorff dimension, which I denote dim sub h, in many contexts, it's equivalent. It can be equivalent to other measures of dimension. So in here, I called it also called, but under certain contexts, it's equal to that case. You have to be careful under what context. But here, we could have also said the Minkowski dimension, if you're familiar with that. We could also say the entropy dimension, which is, I think, more in the physical science, not necessarily the pure math side of it. But then also you have the box counting dimension and the fractal dimension, are kind of layman's terms. In fact, in the actual paper, I used entropy dimension because I thought it sounded cool. That's the only reason. I think my thesis advisor would have probably preferred Minkowski dimension or Hausdorff dimension, but that's just us. But because it was my thesis, he said, yeah, you can call it entropy dimension if you want. Anyway, that's my thesis without proof. I hope you enjoyed what I talked about here. It's kind of amazing just how much of it I could fit on one sheet of paper without proofs. But when you actually write the thing, you do have to be a bit more careful and, prove even like this stuff, like how you show unique representation of your set of your number Z. So It was fun. It took me about a year to write this. I met my thesis advisor usually on a weekly basis, sometimes 2 times a week basis, when we were getting closer and closer to printing the result and sending it to the publisher. In fact, this thesis matriculated into a paper that I wrote with him during the pandemic, and that paper was recently cited, which was kind of exciting. I think it was cited just a few months ago by the time of this recording. He texted me that morning when I was on my way to work, and he said, "Hey, we got a citation." I was like, "Yay, I can put that on a resume." So it's interesting. It's fun stuff. Anyway, that's pretty much all I have to say. And I guess I will mention this at the end. Part of a perk of being in graduate school is that you get to go on conferences, and I have a conference this weekend. So I get to fly out of state and visit people at a new university and see what they're doing. And it's a geometry conference, so I'm pretty excited about it. Anyway, so I'll probably post some pictures of my stay at the university. So stay tuned.